Iceland is fortunate for geothermal resources because it's a very active area volcanically, and it lies on the mid-Atlantic ridge and is being rifted apart by plate motion as the mid-Atlantic ridge is spreading horizontally at about an inch or two a year. And this is the reason that there's a lot of volcanic activity. And if you look at the world map of the oceans, you'll see that these mid-ocean ridges circle the world and have a length of more than 60,000 kilometers. And there are many volcanoes associated with them, not only the ones in Iceland, but for example in the Azores and Reunion Island and so on. And when we look at the heat flow at the surface of the Earth coming from the interior, the largest part of it is coming through the mid-ocean ridges. So we know that the mid-ocean ridges have all that volcanic activity and are also very hot. And also there's a lot of reaction between water and heat, we call hydrothermal activity on the mid-ocean ridges. In fact, so much that we estimate that a volume of water equal to that of the oceans, the whole oceans, goes through the ocean ridges in about 1.5 million years. And as many of you know, there are very interesting hot springs on ocean ridges, the so-called black smokers, which were only discovered in about 1975 and then have been found to occur throughout all of the world's mid-ocean ridge spreading centers, where we have discharge of very hot fluid, which when it encounters the cold seawater precipitates various minerals, particularly black minerals, the sulfides, and that's why they're called black smokers. Interesting biologically because there's very specialized organisms that take advantage of the energy source that these black smokers create. So you have a lot of bacteria that metabolize the sulfides and get their energy from that, and they're the basis of a food chain. And so these are very interesting scientifically. But when one thinks about the fact that most of the heat output is occurring on the mid-ocean ridges, we began to speculate if it might be possible to use that commercially. Now, Iceland has around 600 megawatts of installed geothermal capacity, which is about the same size as a coal-fired plant, and it gets 60% of its electrical demand from hydro and the rest from geothermal. And something like 97% of the houses in Iceland are heated by geothermal hot water. So the Icelanders have learned how to utilize this resource, all the heat that's being put out by volcanic activity in Iceland. And so we decided that we would try to think how could this be developed in the future by drilling much deeper wells than are typically being drilled to get much high energy output per well. The typical geothermal well in Iceland produces enough steam to be used to generate about 5 to 8 megawatts or million watts of electricity. But we thought by drilling much deeper wells we could get much higher output and possibly increase the output by a factor of 10. And that experiment was begun in 2009. We drilled a well that got temperatures of 450 degrees centigrade at the surface and had a power output equivalent to almost 40 megawatts. We didn't achieve exactly what we wanted because we had a very interesting problem. At only a 2,000 meter depth, or approximately 7,000 feet, molten rock started flowing into the well. And so we stopped drilling and completed the well to produce energy from just above that molten rock. And as I told you, it's the hottest geothermal well in the world, capable of producing about 38 to 40 megawatts. But we want to continue these experiments because our ultimate goal is to get deep enough and high enough temperatures in drilling to produce supercritical water. So perhaps you could begin thinking about what supercritical water is. As you know, the boiling point of water varies according to where you are above the surface of the earth or above sea level. Water boils at lower temperatures on mountaintops than it does at sea level. Conversely, if we go higher in pressure, the boiling point of water increases. And as you go up in pressure, not only does the boiling point of water increase, but the differences in physical properties such as density between water and steam become less and less until at a particular temperature called the critical point they merge. So there's only a single fluid, and that happens at 374 degrees Celsius at a pressure of 220 bars, approximately 220 atmospheres, where you have supercritical water, a single fluid which has a very high heat content or enthalpy. Enthalpy just means the heat content per unit mass, usually measured in joules per gram or kilojoules per kilogram. And so we aim to produce supercritical water. The reason is supercritical water not only has very high heat content and enthalpy, but it has very favorable physical properties. The ratio between buoyancy forces and viscous forces, it changes by order of magnitude, so we anticipate not only having a much higher energy output per unit mass of supercritical fluid, but also much higher flow rates. And that's why our modeling suggested we could increase the power output of a geothermal well by a factor of 10.